Hi everyone, we're solving this chemistry paper today. This is 9701 paper 11, May June 2023. The time is 1 hour 15 minutes. I plan to solve paper 13 after this video, so I'll just put a link at the end of the video when we're done solving that. So before we begin, let's take a look at the threshold. So for this particular paper, this is the threshold. The maximum mark is 40, A was at 28, B was at 26, C 21, D 17, and E at 13. So let's write that down. Out of a maximum mark of 40, A was at 28, B 26, C at 21, D at 17, and E at 13. So A star should be at, the discrepancy is too high, like the gap here is 4, it's 5 here, it's 2 here, so yeah, it should probably be around 31 or 2 max. A star was at 31 or 32 at max. Okay, anyway, let's start the paper, but before that, I'd like to talk about my Patreon. We've launched it recently with updated tier prices. So there are 3 tiers currently. The first tier is just for supporting me. The second tier is for access to all these solved question papers from 2002 to 2023 for physics, chemistry, and biology paper 1, 2, 4, and 5, as well as math P1, P3, M1, and S1. You also get access to my notes for AS and A2 physics and chemistry, topic-wise, as well as ad-free videos and requests for question paper solving in my next YouTube video. And for the highest tier, you get access to all the previously stated benefits, as well as your name and the credits on screen on all of my YouTube videos, priority for question paper solving requests, as well as one-on-one video meetings via Google Meet, solving personal problems once or twice a month. So you guys can take a look at that, and let's start the paper. Let's begin. Starting with question number 1. Let's go. Element X has 6 more protons than element Y. Which statement must be correct? Atoms of element Y are smaller than atoms of element X. Not really, because look at the periodic table. I have it over here. Wait. Suppose, I'll give you an example. Suppose, let's take a look at nitrogen. So, nitrogen has 7 protons, then 1, 2, 3, 4, 5, 6. Aluminium, okay, aluminium has 6 more protons than nitrogen. But it is in the third period, so it is bigger than nitrogen, right? So just because you have more protons doesn't mean it will be smaller, okay? So 1A is wrong. B, element X has a full shell of electrons. X has 6 more protons than element Y, okay? So for example, if we talk about nitrogen, 6 more is aluminium. Aluminium does have 2 full shells of electrons, okay? 1s2, 2s2, 2p6. Okay, well, what if we talk about lithium? Okay, so 6 more. 1, 2, 3, 4, 5, 6. Fluorine, it still has 1 full shell, 1s2. Let's talk about hydrogen. So 1, 2, 3, 4, 5, 6. Then we go to nitrogen. Nitrogen also has at least 1 full shell of electrons, which is 1s2. The first shell is full. So yeah, B looks correct. B is probably the answer. Well, let's take a look at C and D though. Element X and Y are in the same group. No, not necessarily. Like we saw nitrogen and aluminium, they are in different groups. They are in the same period. Not necessarily, okay? So C and D are wrong. Which statement explains why calcium has a higher melting point than barium? We are comparing calcium and barium, okay? So basically both of them have a charge of +2. However, as you go down the group, what happens? The size increases, right? Now both of them actually have metallic bonding. So what is metallic bonding? It is the strength of attraction, the electrostatic force of attraction between the cation and the sea of delocalized electrons. So basically, since both of them have metallic bonding, it's just that calcium has stronger metallic bonding. So we can say that this is the answer. Calcium cations are smaller than barium cations, right? So it has more charge density. It has the same charge but smaller size, so greater charge density. As a result, it has stronger attraction for the delocalized electrons. Three statements about potassium and chlorine and their ions are listed. The atomic radius of a potassium atom is greater than the atomic radius of a chlorine atom. So potassium atom and chlorine atom. Okay. So chlorine atom is here and potassium atom is here. So clearly potassium atom has a higher radius because it is in period 3. So yeah, one is in fact correct. So this is excluded, this is also excluded. It needs to be between A and C. So I won't bother checking 2. I'll just go directly to 3. The ionic radius of a potassium ion is greater than the ionic radius of a chloride ion. Okay, so if we think about potassium ion and chloride ion, both of them have the same electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, that is of argon. Now here's the thing, potassium has lost protons, right? It has a charge of +1. So if you think about it that way, on the other hand, chlorine, it has gained an extra electron. As a result, there will be more repulsion in chlorine and the size of chlorine will actually be greater. On the other hand, potassium, since it lost an electron, the protons in the nucleus can pull it more strongly. So the ionic radius of a potassium ion is greater than the ionic radius of a chloride ion. So this is wrong because chloride will have a bigger size, mainly due to the fact that they both have the same electronic configuration, but since chloride has more electrons compared to protons, there will be greater repulsion. Alright, for which equilibrium do both of the equilibrium constants have no units? Okay, so let's check this out. Here it's hi whole square divided by I2 times H2, partial pressure of course. Yeah, here I think, yeah, this is the answer because both match. Even if you do it with concentration, concentration of hi whole square by concentration of h2 into concentration of I2, it will cancel out. Now if you go to B, it won't cancel out because it's 2 divided by 4, so it's wrong. C is 2 divided by 1, so it's wrong. D is 1 divided by 1.5, so that's wrong as well. So 4 is A, number 5. Calcium carbide reacts with water as shown. The data below. The equation show in kilojoule per mole the standard enthalpies of formation of the compounds involved. What is the standard enthalpy change of the reaction shown? Okay, so these are the enthalpies of formation. So if we draw a Hess cycle, it will be like this. Just give me one moment. Here you go. So I need calcium solid, I need H2 gas, I need oxygen gas. Okay, so one arrow over here. Oh, I think I also need carbon. Yeah, I need carbon. Yeah, okay, and one arrow over here. So, and I need half of oxygen. Now hear me out. CaC2, 1 mole of CaC2, so that's minus 60 over here. 1 mole of water, that's minus 286 over here. And on the right, 1 mole of CaO, which is minus 635, and 1 mole of C2H2, which is plus 228. So I need to find out this X. So if you just follow the arrows, it's like this. We can say that minus 60 minus 286 plus X equals to minus 635 plus 228. So if you solve that, 228 minus 635 plus 286 plus 60 gives you an answer of minus 64. Okay, so X is minus 64. Wait, why didn't it match? Let me check again. Minus 635 plus 228 plus 286 plus 60. Minus 61. Sorry, I made a mistake. Okay, so here you go. So 5 should be B. I just checked the mark scheme. It's correct. Okay, let's move on to number 6. Okay, I had this done. Now, in the sodium chloride lattice, the number of chloride ions that surround each sodium ion is called the coordination number of sodium ions. What are the coordination numbers of the sodium ions and the chloride ions in the sodium chloride lattice? Okay, so remember in sodium chloride, It's NaCl, right? So the ratio is 1:1. So it simply can't be A or B. It has to be C or D. Sorry, it can't be D either because the ratio has to be 1:1. Clearly, okay? Because look at it. It's a 3D array. 3D array. So sodium has chloride bound to it above, below, behind the screen, into the screen, to the right, and to the left. It's three-dimensional. And remember, for cations like sodium, magnesium, chloride, silver ions, for all of them, okay, the coordination number will be 6. It's a given fact. Copper, iron, cobalt, nickel, it's always 6. With water, when you dissolve sodium ions in water, also 6 molecules of water will surround it. It's called enthalpy of hydration. You'll learn more about this when you enter A2. But that's the logic basically. So this is going to be 6, okay? Moving on. Number 7, histidine is an amino acid. You'll learn about amino acids in the future. What are the approximate bond angles 1, 2, and 3? Okay, so this carbon is sp2 hybridized. So sp2 hybridized carbons have a bond angle of 120 degrees because it has one double bond and two single bonds. Okay, look at this carbon over here. It is sp3 hybridized, just like methane. So 3 should be 109.5. 3 should be 109.5. Okay, last. Nitrogen, just like ammonia, it has 3 single bonds and 1 lone pair, so it's going to be pyramidal or have an angle of 107 degrees. So I'm going to go with 7b. Number 8, the contact process takes place at a pressure between 100,000 pascals and 200,000 pascals. A catalyst is used. So we use vanadium pentoxide. So a vanadium pentoxide catalyst is used to increase the equilibrium yield of the reaction. Not really. Catalysts do not affect equilibrium, okay? It only increases the rate via an alternate route. Changes in pressure have no effect on the position of the equilibrium. Let's check it out. SO2 plus half O2 is equal to SO3. Since the number of moles do not match on each side, of course a change in pressure will have an effect on equilibrium. B is wrong. The equilibrium yield of the reaction is very high under the conditions used. This is true. The iron catalyst is wrong. It should be V2O5. This is true. The yield is about, it's approximately around 99% approx, yeah. We're at 1 to 2 ATM, right? Moving on to number 9. Till now, I'm finding the variant really simple. Let's see how it evolves over time. Bromine reacts with aqueous sodium hydroxide at 25 degrees Celsius. Reaction 1, bromine plus NaOH gives you NaBr, NaOBr, H2O. The NaOBr formed is unstable at 25 degrees Celsius and further reacts further. So which reactions are disproportionation? So what is a disproportionation reaction? It is a reaction in which the same species is oxidized and reduced simultaneously. That is a disproportionation reaction. Okay, so check this out. Here in reaction 1, bromine was 0. It turned into -1 and +1 over here. So reaction 1 is disproportionation. So this is wrong. Next. Check this out. Here, sodium is +1, oxygen is -2, so bromine is +1. Bromine is -1 here, and check this. Oxygen is -6, Na is +1, bromine is +5. So bromine changed from +1 to -1 as well as +1 to +5. So yes, both of them are disproportionation reactions. Okay, number 10. Which statement is correct? The relative mass of a chlorine 35 atom is 35.5. This is actually wrong because since it's particularly talking about chlorine 35, it should have been 35. Okay, this is wrong. For this particular atom, no. The relative formula mass of CaCO3 is 100.1. I do agree because if you take a look at the booklet over here, the periodic table, let's take. Okay, so CaCO3, we already know a few things. Carbon is 12, oxygen is 16, so 16 times 3 is 48. And calcium, as you can see, is 40.1. So if you add the relative atomic masses of the, you're gonna get the final answer of 100.1. So this is correct. The relative isotopic mass of Mg24C, this is wrong. 24.3 is the relative atomic mass. Okay. And why is A wrong? The relative atomic mass. It should have been the relative isotopic mass of chlorine 35 is 35, something like that. Okay, because the relative atomic mass is like the weighted average mass of all the isotopes of an element, right? Compared to carbon 12, right? That's the logic. The relative molecular mass of O2 is not 16, it's actually 32. You guys know that. Iodine and propanone react according to the following equation. If the concentration of propanone is increased, keeping the total reaction volume constant, the initial rate of the reaction also increases. What could be the reason for this? A greater proportion of collisions are successful at the higher concentration. If we increase the concentration, keeping the total reaction volume constant, initial rate. Okay, this is wrong. They are further apart at higher concentration. They don't have more energy at higher concentration. Now it's between A and D. A greater proportion of collisions are successful. There are more collisions per second between particles at the higher concentration. A greater proportion of collisions are successful. Okay, I think the best answer, the better answer is D. Because let me tell you why A is not correct. Because even if you increase the concentration, there will be more collisions now. But look, the proportion will still be the same. For example, before, if 100 molecules collided, maybe 10 were successful. What was the proportion? 10%. Now if 1000 molecules react, okay, now 100 molecules will be successful, so it's still 10%. So the proportional percentage remains constant. However, the number of collisions increases, which leads to a greater number of successful collisions. That's the logic. All right. Number 12, four successive ionization energies are shown in which group of the periodic table is E. Okay, so as you can see, element E is in period 3. Let me bring the periodic table again. So where were we? Right. So we are looking for a big jump. There is no big jump from 5 to 6 or 6 to 7 or 7 to 8. So clearly it is not in the 5th period, nor the 6th, nor 7th, nor 8th. I meant it's not in 15, it's not in 16, it's not in 17, it's not in 18. So this was a trick question. Not 15, not 16, not 17. It has to be 14 then. Maybe the 4th eye was something like, 8K and then jumped to 16K, okay? So it's more than meets the eye. All right? In this question, you should assume that the gas formed behaves as an ideal gas. So a 1.7 gram sample of Mg reacts with 50 cm cube of 2.2 mol protein to HCl. Which volume of gas is produced measured under these conditions? Okay, let's try. Let's see. Magnesium plus HCl reacts to form H2 plus MgCl2. So the molar ratio will be like this, 2. Yeah, that's all. That's all. Okay, so I want to find out this gas over here. So 1.7 gram of magnesium. So this is 1.7, and we know that the AR of magnesium is 24.3. So 1.7 by 24.3, how much is that? 1.7 by 24.3 is 0.06, 0.07 basically. 0.069959, like that. Okay. And about HCl, what is it? The concentration or the moles of HCl is going to be 50 by 1000 into 2.2, according to this data. 50 by 1000 into 2.2 gives you a value of 0.11. So yeah, we have 0.11 over here moles, and we have 0.07 here. So according to the molar ratio, right, we should be having 0.07 times 2, 0.14 moles of HCl, but we don't. Okay, that means HCl is in fact the limiting reagent, because I actually needed 0.14 moles of HCl, but I have 0.11 moles of HCl. Okay, so magnesium is in excess and HCl is the limiting reagent, so we need to work with the limiting reagent, okay, not the one in excess. Okay, so according to HCl, how many moles of H2 will be produced? 0.11 divided by 2, which is 0.055. Now what is the volume of gas produced under these conditions? Let's go for it. So we know that wait, we know that PV equals to nRT, right? We know that PV equals to nRT, so we need the volume. So V is equal to nRT, which is 0.055 times R 8.31 times temperature 303 divided by, what is it? The pressure, which is 110400. Let's try doing this. So 0.055 times 8.31 times 303 divided by 110400. So V is equal to 1.25 into 10 to the power minus 3 meter cube times 10 to the power 3 gives you an answer of 1.25 dm cube. 1.25 dm cube. So the closest answer for this is actually 1.3 rounded off. That is correct. Now 14. Chlorine dioxide reacts with aqueous sodium hydroxide to produce water and a mixture of two sodium salts. What is the mole ratio? Okay, let's try to do this. Give me 1 second. Actually, I need to move this working up top. Right up. This is bugging me. Okay, so that's the working for 13. Now I'm gonna do it for 14. So for 14, ClO2 reacts with aqueous sodium hydroxide NaOH to produce water H2O and a mixture of two sodium salts. Okay, to produce H2O and a mixture of two sodium salts NaClO2 plus NaClO3. So to balance this, we actually need, you could do trial and error, or you can just go for redox oxidation numbers, which I prefer. Okay, so check this out. So over here, oxygen is of course -4 together, so chlorine is +4. Now over here, what happened to chlorine? Sodium is +1, chlorine, oxygen is -4, so chlorine has to be +3. And on the right, oxygen is -6, sodium is +1, so chlorine has to be +5. So this is also a disproportionation reaction, where one chlorine went from +4 to +5, while another chlorine went from +4 to +3. So it lost one electron, and here it gained one electron. So the ratio should actually be the same, like 1:1, according to this logic, right? That is the answer. So this is how I figure it out. Like, I know that chlorine went from +4 to +5 in one, and in the other one it went from +4 to +3. So as you can see, the ratio is 1:1 for the electron, so that will be the mole ratio in the product mixture as well. See? Next, the temperature of a sample of an inert gas is increased. What effect does this have on the number of molecules with the most probable energy on the number of molecules with higher energy? Okay, so this is a question on the Boltzmann distribution. So if you guys want to see this, let me draw it for you. Wait. So here you go. This is our typical Boltzmann distribution. Now, you guys need to know something. Number of molecules with the most probable energy. So on the x-axis we have energy, and on the y-axis we have the number of particles. Okay, so check this. This is the most probable energy. This is the most probable energy, and this is the number of particles having the most probable energy. Now, if you increase the temperature as mentioned here, what will happen? The graph will shift to the right like this, and it will become flatter. So as a result, compared to before, more particles have higher energy now. Check, more particles have higher energy now, clearly. So number of molecules with higher energy in general, number of molecules with higher energy, this must increase. It can't decrease because the graph has shifted to the right. However, check this. The most probable energy has now changed. It is over here now, and look at the number of particles having that most probable energy. It has decreased from a higher value on the y-axis to a lower value. Okay, so this will be B. 15 is B. So The number of molecules with a higher energy has increased. However, the number of molecules having the most probable energy has decreased. This is something that candidates have to know before you give the exam, okay? All right, moving on to number 16. I also have this solved. For which compound is there the greatest percentage loss of mass on strong heating? Okay, so I'll actually do this for you guys again. I have it done, but I need to explain. So basically trial and error, okay, trial and error. I'll just show you a few, I won't do all of them. So anhydrous calcium carbonate. So check this out. We have CaCO3, which breaks down to form CaO plus CO2. Honestly, this won't be the answer. This one and this one are less likely to be the answers because it's only splitting up to two parts. But for nitrates, it actually gives off nitrogen dioxide gas as well as oxygen gas, which is why B and D are more likely. I'll still show you here. So for which compound is there the greatest percentage loss of mass on heating? So percentage loss of mass. But why don't we try with, any value? Any value works. So for example, check this. What if I take 100 grams? We know that the MR for CaCO3 is 100.1. So if you look at the moles, it's going to be 100 divided by 100.1, which is 0.999. So if you percentage loss of mass, okay, so we need to find out the new mass that is left. This will also be 0.999. And if you look at the MR of CaO, sorry, the mass of CaO now, what will it be? Mass of CaO is going to be 0.999 moles times the MR, which is 40.1 plus 16. So that times 40.1 plus 16 gives you a value of 56 grams. So if you look at the percentage mass, or we could just do the gas, honestly, because now what's it going to be? Percentage loss is equal to 100.1 minus 56 divided by 100.1. Let's do it. Actually, I took 100 grams, right? I have to use 100 grams, my bad, because it's percentage loss of mass. So 100 minus calculated answer divided by 100. It gives me a value of 44%, 43.95, which is 44%. So 44% mass loss for number one. Now look at number D though, D, anhydrous magnesium nitrate. So what happened in magnesium nitrate? It's MgNO3 2. It breaks down to form 2MgO plus 4NO2 plus O2. This is the logic. So what is the percentage loss? It's the two of these combined, right? So what if I take 100 grams of this now? If you look at the MR of magnesium nitrate, it is 24.3 plus nitrogen is 14. 14 times 2 is 28 plus 316 is a 48. 48 plus 48. How much is that? That is 24.3 plus 28 plus 48 plus 48 is 148.3. Okay, so let's find the moles. That's 100 divided by 148.3. So 100 by answer gives you a value of 0.674. 0.674. Okay, now we want to find out the percentage loss in mass. I'll do it the same way, okay? So these two have the same molar ratio, so same moles. I'm just going to find out the mass now. So that is 0.674 times 24.3 plus 16. So into 24.3 plus 16, which is 27.17. So if you look at the percentage mass and loss, it is 100 minus 27.17 divide by 100 into 100%. Okay, so 100 minus 27% divided by 100. Okay, so that is 72.8%. That's a lot. Okay, so clearly nitrates in general will have higher loss, since look, 5 moles of gas are being produced. So it was between B and D in the first place. You can check the other two. 72.8%. I won't bother doing it because the mark scheme answer is D. Typically, the trial and error answers are usually D. Usually, you can try doing it for B and check, but it won't be as high as 72.8. Okay, let's move on to 17. The solids sodium chloride and sodium iodide both react with concentrated sulfuric acid at room temperature. With NaCl, the products are this, and with NaI, the products are NaHSO4, and a lot of products. So basically, clearly, H2SO4 cannot oxidize chloride. Why? Because chlorine is a stronger oxidizing agent than H2SO4. However, H2SO4 can oxidize iodide. Why? Because H2SO4 is a stronger oxidizing agent than iodine. That's the main logic. Okay? Or you can think of it this way: iodide is a stronger reducing agent than chloride. That is why it can reduce sulfuric acid. Okay, so that is the logic behind this. Okay, so chloride ions will displace iodine from solution. Here's the thing: chlorine is a stronger oxidizing agent than iodine. As a result, if you react chlorine with something like potassium iodide, it's going to turn into KCl plus I2. This is the logic. This is possible. But on the other hand, iodide is a stronger reducing agent than chloride. So, iodide can reduce chlorine, but chloride cannot reduce iodine. Understood? So, A is wrong. Next, hydrogen chloride is more volatile than hydrogen iodide. Honestly, this is not a question about volatility. Rather, it's a question about oxidizing and reducing power. Iodide ions are better reducing agent than chloride ions. This is correct. The answer could have been two things. It could either be chlorine is a stronger oxidizing agent than H2SO4, or iodide ions are better reducing agents than chloride ions. Those could be the particular answers. Okay. Next. SiO2 has a melting point of 17-13 degrees Celsius. It reacts with hot NaOH to form a sodium silicate Na2SiO3 and water. No reaction occurs when SiO2 is added to hot H2SO4. What can be deduced from this reaction? Okay, so SiO2 reacts with NaOH. So NaOH is a base, so SiO2 is actually acidic in nature. Okay, no reaction occurs when SiO2 is added to H2SO4. What can be deduced from this information? Right, so H2SO4 is an acid. So since SiO2 cannot react with the acid, it does not have basic properties. So we can say that SiO2 is an acidic salt, acidic oxide actually, because it can only react with base. But since it has such a high melting point, so its structure is obviously giant. Okay, so clearly 18 is C. Moving on to 19, element X has the second largest atomic radius in its period. An atom of X has occupied 3 electrons. Okay, so let's see, where is this? So it's saying that element X has the second largest atomic radius in its period. An atom of X has 3 occupied electron shells only. So 3 occupied shells. So it's clearly not 1, it's clearly not 2, 3 occupied shells. So we are currently here. Now, if you look at the chart for, atomic radius, it's like this. Basically, it decreases over time. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This is the chart for atomic radius approximately. Now, it has the second largest atomic radius. So second largest. This one is the largest, which is sodium. And this is magnesium then. So we are clearly talking about magnesium in the third period. So it is the oxide, magnesium oxide we're talking about. So magnesium oxide. So what's its nature? Its oxide is shaken with water. So it will result in an alkali, magnesium hydroxide. So clearly it's not A or B, it's between C and D. And it's not that alkaline. It's not, maybe if it was sodium, NaOH could be like 13 or 14. But since it's magnesium, the resulting solution will have a pH of 9. Okay, so that is your answer. Okay. Next, which emission from an internal combustion engine contributes to the erosion of marble statues? Okay, so acid rain results in the erosion of marble statues. So we know that uh, NOx, NO and NO2, these are released from um, the combustion engines, which actually catalyzes the formation of acid rain by converting SO2 to SO3, and that actually results in erosion of marble statues. Okay, question 21. The diagram shows the melting points of 8 elements with consecutive atomic numbers. Which element could be sodium? So consecutive um, atomic numbers. So from sodium to magnesium to aluminum, what happens? The strength of metallic bonding actually increases. Okay, the strength of metallic bonding actually increases. And clearly over here, as you can see, B, the one with the lowest one, is probably a noble gas. Okay, it's probably a noble gas. So probably it's neon. That's neon. Then we have sodium, right? Followed by magnesium. This is probably neon, okay? Followed by sodium, magnesium, and aluminum. The jump from 2 plus to 3 plus isn't that high. You should always remember that. It's an increase, but not that high. But the jump from Na plus to 2 plus delocalized electrons actually increases the metallic bonding almost twofold, basically. So yeah, I'm gonna go with C. I just saw the trend where I can see three direct increases, which I identified as C, D, and the dot after it. And the jump from the first one will be much higher. And the lowest one is probably a noble gas. That's how it works, okay? And clearly, check this out. The one after aluminum, it has such a high melting point. It is clearly silicon. This one over here is silicon because it has a giant structure, right? Giant covalent structure. Okay, moving on to question 22. The boiling points of bromine, ICl, IBr are given in the table. Which row explains why the boiling point of ICl is greater than Br2, why the boiling point of IBr is greater than ICl? Okay, so here you guys gotta understand that we only have intermolecular force of attraction that actually determines your melting and boiling points actually. So if you think about it this way, bromine doesn't have a dipole. It can only have instantaneous dipoles, but ICl on the other hand has permanent dipoles, right? Because there's a difference in polarity. So the reason is ICl has permanent dipoles for the first one, and here IBr and ICl, both of them have permanent dipoles. It's just that uh, if you think about it, like IBr has a boiling point of 116 compared to 97 in ICl. Why is that? Both of them have permanent dipoles, but it's just that you know something is stronger in the case of IBr. Now, if you look at the periodic table again, there are a lot of questions based on the periodic table actually. So, chlorine, bromine, and iodine. If you look at the gap, the difference in electronegativity, we have IBr and ICl, right? So the difference in electronegativity between ICl and IBr, which one is higher? ICl has a greater difference in electronegativity, right? ICl has a greater difference in electronegativity. As a result, you know, it should have stronger permanent dipoles, logically, because the difference in electronegativity is higher. That is why um, this is wrong. IBr does not have stronger permanent dipoles because the difference in electronegativity isn't greater than ICl, right? Because I showed you in the periodic table. So what could the answer be? The answer must be IBr has stronger instantaneous dipole induced dipole forces. There is no other reason, okay? So I'll break this down again. Basically, ICl has permanent dipoles while bromine does not have permanent dipoles, which is why ICl is stronger than Br, more melting boiling point. Next, IBr and ICl. The gap between ICl in the periodic table is greater than IBr. So basically, ICl should logically have stronger permanent dipoles, not IBr, which is why this is wrong. So the only possible explanation can be that IBr has stronger instantaneous dipole induced dipoles. Why though? What is the logic behind this? Because bromine has a I and Br, they have a greater number of electrons, which leads to the easier formation of induced dipoles. Moving on. Question 23. A solution contains both magnesium 2 plus and Sr2 plus at the same concentration. The solution is divided into two equal portions. Aqueous sodium hydroxide is added dropwise to one portion and dilute sulfuric acid is added dropwise to the other portion. Which row is correct? Precipitate seen first when NaOH is added. Okay. So hear me out. You guys got to understand that magnesium sulfate is actually soluble. Okay, magnesium sulfate is soluble, so it can't be the answer. It has to be strontium sulfate. Next, on the other hand, barium hydroxide and strontium hydroxide are soluble, and magnesium hydroxide is insoluble. It's a precipitate. So 23 is B. That is the logic. Okay. Next, structural isomerism and stereoisomerism should be considered when answering this question. If a molecule contains two non-identical chiral carbon atoms, four optical isomers exist. How many isomers are there with the molecular formula? Okay, so we are talking about two non-identical chiral carbon atoms. So 2 square is 4. Molecular formula C7H14O, 5-membered ring, tertiary alcohol group. Okay, so C, 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 C. So this is a 5-member ring. All right, so that's the first thing that we need to do. Next, we need a tertiary alcohol group. So if I try doing this OH over here, this already has two alkyl groups. This carbon already has two alkyl groups, so I need another C over here. Okay, so I can give CH3 over here. So how many carbons did I use? I used 1, 2, 3, 4, 5, 6 in total. So now what's the last step? I need to use the last one and ensure that, okay, but we need to talk about all the isomers. So let's just go step by step. Let's see how it goes. Okay, so first, for my first isomer, honestly, I can use skeletal formulas if that's fine with you guys. Like I can go for this CH3 over here. It should be CH, 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 like this, okay? Actually CH2, right? CH2, 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 and there should be another H over here. So that's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so the same compound, if I draw a skeletal version, it will look like this. CH3 over here, there's another CH3 over here, and then OH over here, because I need this carbon over here to be tertiary. Okay, so this is chiral, this is also chiral. As a result, this has resulted in how many isomers in total? 4. Okay, so let's draw another one then. Honestly, if I try doing this, what if I try doing this? Wait, C. What if I draw the C over here? No, I don't think I can give the OH at the end, right? There's no way, because then it would turn into a secondary alcohol, and I have 1, 2, 3, 4, 5, 6, 7, 8. I can't use 8. So the OH has to be attached to the ring, or else there's no way of forming it. Okay, let's try another one. What if I go for this? I attach the OH here, fine. Now what if I give a branched chain over here like this? There you go. So how many chiral carbons does this have? Just 1. So 2 isomers over here. Okay, so that's 2 plus 4, which is 6. 5-member ring tertiary alcohol group. Okay, let's go to the next one then. So OH over here, one hand over here, fine. Now what if I attach the CH3 over here? So this is chiral again, right? This is chiral again, and this is also chiral. So how much is that exactly? That is 4. So actually here in the previous one, we can't actually consider this one to have 2 isomers. The logic being, check this. check this carbon over here. If you go to the left and if you go to the right, what's happening actually? Aren't you ending up with the same compound? Look, you have CH2 over here, CH2 over here, you have CH2 over here as well as CH2 over here. It is symmetrical about this point. So you aren't actually ending up with two isomers because this is not a chiral carbon. To be a chiral carbon, you need four different groups attached to the carbon that is we're talking about currently. But here clearly these are identical groups on right and left, so we just have one isomer. Okay, and that's it. It should be 9. I'm not drawing the other ones because I'll show you why. Check this. If you draw something like this, this is the same compound as this one over here. Okay, it's the same thing. They don't have anything that's different, it's just inverted. So in total 4 plus 4 plus 1, so it gives us an answer of 9C. Next, number 25. Which reagent will react with pentanthreol to give a mixture of stereoisomers? So pentanthreol, let's take a look. 1 second. Pentanthreol, CH3, CH2, CO, CH2, CH3. Acidified potassium dichromate. Ketones cannot be oxidized. Concentrated sulfuric acid. Actually, oh, it's pentanthreol. My bad. Sorry. Pentanthreol. So that's CH3 CHOH. So if you give acidified potassium dichromate, it will turn into pentanone, which is only one compound, no stereoisomers. So A is wrong. Next, for B, if you give concentrated, will react with pentanthreol to give a mixture of stereoisomers. Okay, so what does concentrated sulfuric acid do? It's going to dehydrate this alcohol to form CH3, CH2. It can form on any side, CH, CH3. So this is, what is it actually? Pentoene, which does have cis-trans isomerism, so B is the correct answer. Now, what about HCl? If you give HCl, you'll simply get, um, basically 3-chloropentane. And if you give ethanoic acid in the presence of a little concentrated H2SO4, you get the ester between ethanoic acid and pentanthreol. But you wouldn't get any stereoisomers, okay, because you wouldn't get any chiral carbons. Number 26 now. An organic molecule W contains 3 carbon atoms. It requires 4.5 molecules of oxygen for complete combustion. What could W be? Okay, 3 carbon atoms. So let's do the math. Trial and error. Propane, CH3, or we can just go for C3H8 for propane, plus O2 gives you CO2 plus H2O. So it's 3 over here, 4 over here. So 3 to the 6. 6 plus 4 is 5. Sorry, 6 plus 4 is 10. So it should be 5 over here. So that's 10. So A is wrong. Propanoic acid. Propanoic acid is CH3, CH2COOH plus O2 to give CO2 plus H2O. So it should be 3 again over here, then 1 2 3 4 5 6. So 3 over here. So 3 plus 6 is 9. I already have 2 here. So I need 7. So 7 by 2, 3.5, close but not there. It's probably D, because it's trial and error. Propane 1 all. What is that? CH3, CH2, CH2OH plus O2 gives you CO2 plus H2O. So that is 1 2 3 3 over here. H3 4 5 6 7 8. So that's 4 here. So 4 plus 6 is 10, but we already have 1 here. So we need 9 by 2 over here, or 4.5. So D is our answer. See, both of the trial and error ones are D. 27. Which equation represents a reaction that proceeds through initiation, propagation, and termination steps? Okay. All right. Oh, basically they are talking about free radical substitution here. So clearly that's A. Chlorine plus, butane gives you a mixture of compounds. This is free radical substitution with an alkane plus chlorine, okay? 28. Structure isomerism and stereoisomerism should be considered when answering this question. A set of isomeric hydrocarbons are given. Okay, so let's see. all contain 14.3% by mass of hydrogen. All react with bromine by addition of 0.280 gram of each hydrocarbon, reacting with 0.799 of bromine. This is such an annoying sum. Okay, so it's a hydrocarbon, so it's just CH. So it's 14.3 over here, so that should be 100 minus 14.3, which is 85.7. So by 1 by 12, 7.14, 14.3. So 14.3 divided by answer, which is 2. So it's 1:2 ratio. Okay, so now we know that all this isomeric set actually will react with bromine, 0.280 grams of each hydrocarbon, reacting with 0.799 grams of bromine. So we know that this is an alkene, right? Because it has a ratio of 1:2 CH2. So it's basically going to be like this: bromine plus CxH2x will give us the product, and we know that their molar ratio is 1:1. So what's the mass of bromine? It's 0.799, and if you look at the mass of bromine, it's 79.9 each atom. So what's the MR of bromine? It's 79.9 times 2, which is 159.8. So moles of bromine will actually be 0.799 by 159.8, which gives us an answer of 5 into 10 to the power minus 3. So this also has the same number of moles, 1:1 ratio, but a mass of 0.280. Fine. Now if you want to find out the moles, we know that moles is equal to mass by MR. So the MR will be mass by moles, which is 0.280 divided by 5 into 10 power minus 3. Let's see. 0.280 divided by answer, which is 56. MR is actually 56. So fine, we have the MR of this compound. So let's try. If you do C3H6, what's the MR? 3 times 12 plus 6, which is 42. So that's not right. C4H8, how much is it? 4 times 12 plus 8, which is 56. Okay, we have our answer. So this compound is actually butene. Now it may be but1-ene or but2-ene. That's the tricky part. Okay, so why don't we move this over here and I'll solve it for you. Let's go. So butene. So let's try with but1-ene first. CH3, CH2, CH, CH3. Now after addition of bromine, we are going to end up with CH3, CH2, CHBr. Sorry, this should be CH2. Wait, let me fix it. CH2, CH2Br. So this is chiral, so we actually end up with 2 isomers over here. Okay, now what about but2-ene? That is CH3, CH, CH, CH3. If you add bromine, you end up with CH3, CHBr, CHBr, CH3. So wait, what are they exactly asking? I need to figure this out. What is the maximum number of isomeric compounds in this set? So they're not talking about the product. My bad. They're not talking about the product itself, rather the reactants. Okay, so this is one. This is one of the possible reactants, the isomeric hydrocarbons actually. So this is another one, CH3, CH, CH, CH3, and this has cis-trans isomerism, so this will count as 2. And what about the last one? The last one can be written like this: CH2, one CH3 over here, another CH3 over here. Okay, and this does not have cis-trans isomerism. So in total, this but2-ene, this set of isomeric hydrocarbons, it's 4 in total. So I'm gonna go with my answer, which is C. All right, that's good. So yeah, it's a different type of question actually. I haven't seen this before. Rather challenging. Moving on to the next one. Which row describes the solvent used and the type of reaction when bromoethane CH3 CH2Br reacts with NaOH to form ethene. So this is clearly an elimination reaction, and we need it to be in ethanol. Ethanolic NaOH results in an elimination reaction. Which row? Because if it was water, it would be a substitution reaction, hydrolysis. We'd get ethanol. Which row describes the type of reaction that occurs when propan-1-ol reacts to form the named carbon-containing product. Propan-1-ol. CH3, CH2, CH2OH. When propan-1-ol um, reacts with 1-chloropropane, the orange propan reacts to form the named. Okay, so propan-1-ol reacts to form the named product. Fine. Propan-1-ol to 1-chloropropane. So clearly, this is not addition, rather it's substitution. Okay, so 30 is wrong. Substitution by HCl or something. PCl5, PCl3. Carbon monoxide. Propan-1-ol to carbon monoxide. It will be incomplete combustion, because if it was complete combustion, we would get CO2 instead. Propene. Now this forms propene, CH3, CH2. This is an elimination reaction. It is dehydration of propan-1-ol using pumice or concentrate H2SO4, H3PO4, etc. 30C is correct. 31. Which statement describes what happens when 2-chloro-2-methylpropane? Okay, so CH3, C, Cl over here, CH3 over here, CH3 over here. So 2-chloro-2-methylpropane is warmed with NaOH aqueous. So it will be a nucleophilic substitution reaction. However, since it's a tertiary alcohol and so stable, it will proceed by the SN1 mechanism, because it's a tertiary halogenoalkane, right? So 31 is in fact C. Mostly by SN1 mechanism. How many structurally isomeric secondary alcohols are there with C5H12O? Okay, only structural isomers. So CH3, CH2, 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 CH2OH. I'll draw using skeletal, okay? It'll be easier for me. 1, 2, 3, 4, 5. Propan-1-ol. 1, 2, 3, 4, 5. Now propan-2-ol. Then 1, 2, 3, 4, 5. Propan-3-ol. So these are 3. Okay, next branching now. So structure isomers though. Oh, we can only use secondary alcohols. Sorry, I did not see that. So only secondary alcohols. So this is excluded. These two count. Next, I can keep it here and do some branching. For example, I can keep the OH over here and do some branching. For example, I can put this over here, one hand over here, one hand over here. Okay, so that is another one. And probably that's it, because if you try to do the same thing over here, check this. If you try to do the same thing, like 1, 2, if you try to move this part over here somewhere else, this compound ends up being the same one, like this, right? So the final answer is 3, as it's secondary alcohols only. Okay, next, which reagent can confirm the presence of a carbonyl group in an organic compound, that is actually 2,4-DNPH, does not distinguish between aldehydes and ketones? Okay, so it has to be 2,4-DNPH. It only tells us whether it's a carbonyl like aldehyde or ketone, but not specifically ketone or aldehyde. Which compound gives a positive test with alkaline aqueous iodine but does not show optic isomerism? Okay, so this is a methyl ketone. It is positive for methyl ketones. So CH3CO, CH2, CH2OH, and in fact this does not have any chiral carbons. Look, it has a methyl ketone but no chiral carbons. So 34 is A. 36. Okay, let's do this one. What is it? 2 samples of compound X were treated separately with different reagents. The products of these 2 reactions are shown. So in the first one, what happened? Everything remained the same. Just this aldehyde over here was converted to a carboxylic acid. So this is an oxidation reaction. And in reaction 2, what happened? The ketone and aldehyde were reduced to form a secondary and primary alcohol respectively. So this is reduction. So we can reduce this using NaBH4 or LiAlH4, and we can oxidize, you know, the aldehyde to carboxylic acid using Tollens reagent. So Na was out of the equation. It was between B and D. Why not B though? Because if we use sodium dichromate, then this secondary alcohol would also be oxidized to ketones. So since that remained the same, that is why we used Tollens reagent. A lot of students forget that Tollens and Fehling's reagents are actually oxidizing agents. They only oxidize aldehydes but not ketones. But they are not strong enough to oxidize primary and secondary alcohols. That's the logic behind Tollens and Fehling's. In Tollens we get a silver mirror, and in Fehling's we get a brick red PPT. Which method could produce butanoic acid? Acid-base reaction involving this. Let's see, CH3, CH2, CH2, COO minus Na plus. So if you add an acid, if you acidify this solution, it will turn into CH3, CH2, CH2, COH. It turns into butanoic acid. This is the salt state. It's sodium ethanoate. If you acidify it enough, then yes, it does turn into butanoic acid. If you hydrolyze B, it actually turns into CH3, CH2, CH2, CH2COH, right? So which is pentanoic acid, which is why this is wrong. Over here we are gonna get propanoic acid. Over here we are gonna get 1, 2, 3 also propanoic acid. So those are wrong. Next 37. Which ester may be hydrolyzed to produce two products, one of which may be reduced to the other? Okay, interesting. So here we are gonna get on the right side methanol, on the left side propanoic acid. So that's impossible. Let's check B out. So for B it is CH3, CH, CH3, COO, CH2, CH, one CH3 over here, one CH3 over here. If you do hydrolyze this, on one end we'll get CH3, CH. These look like mirror images, by the way. COOH, and over here we are getting CH2OH, followed by CH, CH3, CH3. Now this part is the same. And yes, if we do reduce this carboxylic acid, we are going to end up with the same product. It's going to turn into 2-methyl propanol. 2-methyl propanol. So yes, B is our answer. B is the correct answer. You can reduce carboxylic acids using LiLH4 to form primary alcohols. Okay. Next, two compounds X and Y are mixed, and a little concentrated H2SO4 is added. Ester Z is formed. So which two compounds could be X and Y? So this is the ester bond. I cut it. This is the ester bond, and this is the ester bond. So this is our. These are our ester bonds. This is one alcohol. This is another alcohol. Okay. Oh, but two compounds only. They said that there are two compounds. Interesting question, actually. So this is our acid part. Okay. Similarly, this is also the acid part. This is also the acid part. This one is methanoic acid, which is HCOH. This one is also methanoic acid, which is HCOH. And this is actually one. Sorry, this isn't methanoic acid. My bad, guys. My bad. Since it has two carbons, 1, 2, it's actually ethanoic acid. Ethanoic acid, and this is 1, 2, 3 propanoic acid. So this is CH3COH. Similarly, this is also CH3COH, and on the top over here we have CH3CH2COH. Okay. Now in the middle, what do we have actually? Check this. If I draw the compound again, OH, this will be CH2. Over here we have a carbon. I'll actually draw the skeletal one first. Wait. So O, there you go. Over here, here. Oh, you can give the ages. So if I break down this compound, we actually end up with this is the same as CH2OH. Wait up. Then I'm over here. Then I go down. Carbon over here. I have another OH over here. Okay. The 1H, and here I have CH2OH. So this is the alcohol that I'm looking for because it's the alcohol component. The one with oxygen is always the alcohol component. Okay, so I'm basically looking for this compound. It's like a triol, right? It has an alcohol group in the first, second, and third. Um, carbon basically. However, then we would actually need three carboxylic acids, right? It's a bit strange because we'd need two ethanoic acids and one propanoic acid, which doesn't make sense. Okay, which doesn't make sense actually. So I'm thinking that it might be one ester with two alcohol groups mixed with ethanoic acid. Okay, because here clearly A and B are wrong because there's no way that it's this alcohol. So it's between C and D. And if you use D over here, the compound that I drew does match with mine over here, right? However, then we wouldn't be getting this part. It would have been correct if this part was missing, then it would be the correct answer because we would have ethanoic acid throughout the diagram. However, the issue is we have propanoic acid on top. So I think the correct answer should be C because check this. If I draw this compound over here, I'll show you. What is this compound? Check. Okay, so it's basically, if I draw it carefully, it's CH2OH. I'm done with this part. Followed by CHOH. Fine. Next, this part. See, I told you. CH2 followed by CH2O CO CH2 CH3. So this compound already had an ester included, right? It already had this part. And when we added the carboxylic acid, one ester formed here, one ester bond formed here. And that is how we ended up with ester Z. But there is an issue in this particular question because we did add a little bit of concentrated H2SO4. There was a chance that, this bond might have broken down. Maybe we couldn't get this product. So yeah, there is an issue in this question, but it is quite challenging. It really tests your skills as an organic chemist. So if you got this right, you're really smart. Next. The diagram shows a section of a polymer molecule. What monomer will produce this? Okay, so let's just draw it as it is. Come on. So the trick is draw the double bond like this. Draw the double bond like this. Then one H on top, one H like this. Oh, this is rather challenging because after forming the repeat units or the polymer, you're not supposed to have double bonds. But if you do have a double bond in between, that means your monomer had two double bonds. And in this particular scenario, check this, it's very strange because this one in the middle is not supposed to exist. This is a particular pattern. The answer is D. In this particular pattern, what happens is, well, as you can see when I draw this diagram, check this out. It's CH2. Wait, let me draw it like this. CH, 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 HH. Okay, so what happens is when this particular compound, this comes repeatedly, when it forms a polymer, you know that the double bond has to break, right? So yes, these new bonds form on each end. However, check this out. This carbon had four bonds before, but now one hand is free. So what these two carbons will do is they will form another bond in between them. Okay, when the repeat units form, that is exactly this middle bond which did not exist initially. So that happens and yeah, we end up with this particular compound. This has been coming repeatedly since 2020 as far as I know. So yeah, please and you could cancel out A, B, and C because they only have a single bond, right? Single double bond. So that doesn't make sense. You wouldn't end up with a double bond after forming the polymer, yeah? Okay, last 40. There are two naturally occurring isotopes of bromine. One isotope has 44 neutrons, the other has 46. Ignoring fragments, how many peaks are there in the mass spectrum of particularly sweet C12H1 and Br3? Okay, no fragments, right? Fine. So hear me out. What are the combinations? So C12H1. So let's start with this. Br, we have 79 and 81, right? 79 and 81. Br 79 and Br 81. So this is one combination, Br 79, 79, 79. Then we also have the topmost, the highest combination is Br 81, Br 81, Br 81. Okay, so this will have a mass of 6 more than this one. Okay, then what's the other combination? Two Br 79s and one Br 81. It doesn't matter where we put this. Okay, it might be in the middle or the first one, doesn't really matter. Then what do we have? One Br 79 but two Br 81s. Okay, because this is fixed, right? Suppose it's 12 plus 1, which is 13, plus 79 plus 79 plus 79. So that gives you a mass of 250 over here. This will have a mass of 252. This will have a mass of 254. And this will have a mass of 256. So excluding fragments, these are the main compounds that are possible. So there are a total of 4. No more than this, okay? So that is it for the paper. I feel like the inorganic part was relatively easy, but the organic questions were quite difficult. I had to think for a few of them, as I haven't faced those questions before. So the questions have evolved. So I hope you like the content. And yeah, you can consider supporting me on Patreon. So quick shout out to my highest tier patron for the month. We only have Dewa supporting me right now. You can get access to video meetings with me where we solve your personal problems once or twice a month if you subscribe to that tier, as well as all my solved papers and notes. So yeah, I hope this video helped you guys. I'll link the paper for 9701 May June 2023, paper 1 2 up here, and the paper for May June 2023 variant 1 3 down here, and the playlist for chemistry paper 1 up here. And remember to hit the subscribe button. See you guys. Bye bye.